Good morning, ma'am. We are Group 11 and our report is all about induction motors. Induction. Three-phase induction motors are the most common and frequently encountered machines in industry. Simple design, rugged, low price, easy maintenance. Wide range of power ratings, fractional horsepower to 10 MW. Run essentially as constant speed from no load to full load. Its speed depends on the frequency of the power source. Not easy to have a variable speed control. Requires a variable frequency power electronic drive for optional speed control. Construction. An induction motor has two main parts. A stationary stator, consisting of a steel frame that supports hollow cylindrical core constructed from stock laminations, having number of evenly spaced slots providing the space for the stator winding. Construction. A revolving rotor composed of punch laminations stacked to create a series of rotor slots providing space for the rotor winding. One of two types of rotor windings. Conventional three-phase windings made of insulated wire. One rotor, similar to the winding on the stator. Aluminum bus bars shorted together at the ends by two aluminum rings, forming a squirrel cage-shaped circuit, squirrel cage. Two basic design types depending on the rotor design. Squirrel cage conducting bars laid into slots and shorted at both ends by shorting rings. One rotor complete set of three-phase windings exactly as the stator. Usually Y connected, the ends of the three rotor wires are connected to three slip rings on the rotor shaft. In this way, the rotor circuit is accessible. Thank you.
There are two types of rotors. One is the squirrel cage rotor and the other one is the wound rotor. These are another example of rotors. Cutaway in typical wound rotors IM, notice the brushes and the slip rings. So nani siya slip rings and brushes. Muni kalainan sa laing rotors. Rotating magnetic field. Balance 3 pieces winding, etc. Mechanically displaced 120 degrees from each other. Feed by balanced 3-phase source. A rotating magnetic field with a constant magnitude is produced rotating with the speed. Here is the formula. In sync equals 120 FA over P RPM, where F is the supply frequency and P is the number of poles, and in sync is called the synchronous speed in RPM, revolution per minute. Principles of operation. This rotating magnetic field cuts the rotor winding and produces induced voltage in the rotor windings. Due to the fact that the rotor winding are short-circuited, but squirrel cage and wound rotor and induced current flows in the rotor windings. The rotor current produces another magnetic field. A torque produces as a result of the interaction of those two magnetic fields. The formula of the induced torque. T induced or induced torque equals to Kie R times Bs, where the T is induced torque and B R and Bs are magnetic flux densities of the rotor and the stator respectively. Induction motor speed. At what speed will the IM run? Can the IM run at the synchronous speed, and why? If rotor runs at the synchronous speed, which is the same speed of the rotating magnetic field, The rotor will appear stationary to the rotating magnetic field, and the rotating magnetic field will not cut the rotor, so no induced current will flow in the rotor, and no rotor magnetic flux will produce, so no torque is generated, and the rotor speed will fall below the synchronous speed. When the speed falls, the rotating magnetic field will cut the rotor windings, and a torque is produced. So the IM will always run at the speed lower than the synchronous speed. The difference between the motor speed and the synchronous speed is the called slip. In slip equals in sync minus Nm, where the in slip is the slip speed, and the in sync is the speed of magnetic field, and Nm is the mechanical shaft speed of the motor. The slip equals in sync minus Nm over in sync, where the S is the slip, and notice that the rotor runs at synchronous speed, so S equals to 0. If the rotor is stationary, S is equals to 1. Slip may be expressed as percentage by multiplying the above equation by 100%. Notice that the slip is a ratio and doesn't have a unit.
So, good day everyone, especially to you ma'am. I am here in front of you to continue reporting the topic induction motors. So, let us continue in induction motors and transformers. Both induction motor and transformer works on the principle of induced voltage. So, for transformer, voltage applied to the primary windings produce an induced voltage in the secondary windings. For induction motor, voltage applied to the stator windings produce an induced voltage in the rotor windings. So, the difference between induction motors and transformer, in the case of the induction motor, the secondary windings can move. Due to the rotation of the rotor or the secondary winding of induction motor, the induced voltage in it does not have the same frequency of the stator or the primary voltage. So, sa transformer, voltage applied to the primary windings, which means nga ang voltage mo adto sa iyang primary windings para ma-produce yung induced voltage nga mo adto para sa iyang secondary windings, which is ang iyang output sa iyang voltage or sa iyang kurente. So, sa induction motor, kuana voltage apply to the stator na dili na siya primary, kay ang usually mong yun from the word pa lang motor na siya motor sa ilam. So na siya stator niya moadto na siya sa stator windings para maka-produce siya induced voltage parong sa iyang rotor windings. So next is frequency. What would be the frequency of the rotor's induced voltage at any speed? Nm. So mo ni ang kaning common formula sa frequency. Fr is equals to SFE. Nya, when the rotor is blocked, S is equals to 1. So, the frequency of the induced voltage is equal to the supply frequency. And then, on the other hand, if the rotor runs at synchronous speed, so, muna siyang S is equals to 0. Then, the frequency will be 0. Then, ang sunod is ang horsepower. So, horsepower is another unit used to measure mechanical power. It is used to refer the mechanical output power of the motor. Since we as mechanical engineers deal with watts as a unit to measure electrical power, so nana siya relation between horsepower and watts. So, money, 1 horsepower is equals to 746 watts.
Fundamentals of equivalent circuit analysis, emphasizing its role in simplifying complex systems for analysis and design. It defines equivalent circuits as simplified representations using ideal elements like resistor, capacitors, and inductors. The significance lies in simplification for analysis, design optimization, and modeling real-world components. Common elements in equivalent circuits include resistors, capacitors, inductors, voltage sources, and current sources. Applications range from power systems to electronic devices and transmission lines, showcasing its broad utility for system stability, efficiency, and performance optimization. The induction motor is similar to the transformer with the exception that its secondary windings are free to rotate. As we notice in the transformer, it is easier if we can combine these two circuits in one circuit, but there are some difficulties. Power losses in induction machines, emphasizing their impact on overall efficiency and performance within electrical systems. It analyzes the contributing factors including core losses, copper losses, stray losses, and mechanical losses. The implications of higher power losses on machine efficiency, potential heating issues, and overall reliability are discussed, highlighting the importance of optimization in various industrial applications. Mitigation strategies such as selecting quality core materials, optimizing winding designs, and employing advanced cooling techniques are presented as crucial for improving machine efficiency.
For summary of our topic, the induction motor is the most popular type of AC motor because of its simplicity and ease of operation. An induction motor is basically a rotating transformer. Its equivalent circuit is similar to that of a transformer except for the effects of varying speed. An induction motor normally operates at a speed near synchronous speed, but it can never operate at exactly the slip or speed at which the maximum torque occurs can be controlled by varying the motor resistance. Summary continue. Speed control of induction motors can be accomplished by changing the number of poles on the machine, by changing the applied electrical frequency, by changing the rotor resistance in the case of a wound rotor resistance in the case of a wound rotor induction motor. Thank you.